take a moment and look at this. This could go on forever. What you're seeing is a fractal. As satisfying as it may look, it was horror for the mathematicians of the early ages. So much so that they were called monsters due to their complex nature. So what is a fractal, you may ask? A fractal is a never-ending pattern that repeats itself at smaller scales. It is recursively constructed or self-similar in nature. The Cantor set shows us that a single line can be divided forever, like such. The Sierpinski triangle is made by repeatedly removing the middle triangle from its prior generation. Fractals are found more commonly than you might think. Nature is full of fractals.
Even in snowflakes, consider the quote snowflake. To construct it, we take a line, divide it into thirds, and on the middle segment, we make an equilateral triangle and remove the base. We repeat the process to get this.
Fun fact, it has an infinite perimeter and a finite area.
But self-similarity is not a sufficient condition to label a pattern as a fractal. That's where dimensions kick in. We say a line is one-dimensional because it has just one dimension, that is, its length. A rectangle is two-dimensional because it has length and breadth, and a cuboid is three-dimensional because it has length, breadth, and height. This is a valid notion, but let's talk mathematically.
We break a line segment into 4 self-similar intervals, each of which can be magnified by a factor of 4 to yield the original segment.
A line can be broken down into n self-similar pieces, each with magnification factor n.
This is the case with a square and this with a cube.
So in conclusion, the magnification factor raised to the dimension is equal to the number of self-similar pieces.
Thus, we see a way of specifying the dimension of a self-similar object.
Coming back to the quote snowflake. At the second step, we have 4 smaller self-similar pieces with a magnification factor 3 because each piece is 1/3 of the original. On applying this, we get 3 raised to power the dimension of the quote snowflake is equal to 4. D is equal to log 4 base 3.
So it is necessary for a fractal to have a dimension called the Hausdorff dimension, which is mostly non-integer. The father of fractal geometry, Sir Mandelbrot, exactly defined a fractal as a shape
whose Hausdorff dimension lies in between its topological and Euclidean dimension.
The Euclidean dimensions are the traditional dimensions that we speak of, and this discussion of topological dimensions is beyond the scope of this video. It is worth noting that both dimensions have integer values only. The dimension of a fractal is a measure of its roughness. A fractal of dimension 1.9 is rougher than a fractal of dimension 1.5. While solving a problem of noise errors during data transmission in phone lines, Mandelbrot noticed
Whether the graph represented data over 1 day, 1 hour, or 1 second, the pattern of disturbance was similar.
My point is, for such a random process, there is an underlying fractal pattern. Fractals are graphs of almost all chaotic processes, from crystal growth to galaxy formation. We have just scratched the surface of discoveries relating to fractals. So who's ready for the next breakthrough?